Thank you so much. Thank you. Thank you. Ah, thank you so much. Right, well, look, thank you so much for coming. We're going to talk about gas. What is it? What can it do? What can it do for us? Do we care? Hopefully, we'll answer some of those questions in this misty, smoky atmosphere. But first, I need to tell you something about something much more mundane, perhaps you think, which is this candle. And this is a flashback to a demo done back here 200 years ago. If we turn the lights down a little bit. Yes. Now, this is more 19th century, right? Faraday here, the beginning of the Royal Institution, the beginning of the idea that people should know about science, that people are even interested in science, and people might be able to help science go forward. New scientists can come on the scene because they see some demo at the Royal Institution. And this place has been the fulcrum for showing people science by demonstrating. It's the best place in the world to do it. So it's just great to be able to do it for you today. But why a candle? That seems a little bit, mundane. Oh, it's a balloon. And, but no, it isn't. And I want to just point something out to you here, that a candle, it holds so much interesting science, as Faraday pointed out 200 years ago. And next time you're really bored at a dinner party, try to remember some of what we're talking about now, okay? Someone says, moaning on at you, blah, 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 I bought these stocks, and you just look at the candle, and you go, wow, so the candle's a particular shape, and it's got lots of stuff going on in it. And the ancients thought that fire, which is the stuff coming out of the candle, was an element. They thought there were 4 elements: earth, air, wind, and fire. And this is fire, an element, a substance, clearly a substance, right? Because it's so different from everything else. But it's not. In fact, they also thought there was a 5th element, quintessence, or ether. And I'm not going to talk about that today, but it's a really interesting, different part of the book, which we can talk about later in the questions if anyone wants to talk about. But if we talk about fire, they really thought this is, and it's not an unreasonable thing to think, because some things burn, most things don't burn. And this stuff destroys things. It's an elemental force. And here you are at a dinner party looking at this elemental force and thinking, yeah, but it's not an element, is it? And then you start noticing other things. You say, look, there's different colors. There's yellow, and there's a sort of black bit. And then there's a blue bit. And I don't know if we can see this blue bit, but there's some blue flame. And what is that? So obviously, a candle we now know is a gas technology. It's a phenomenon. And it's when you get a vapor, in this case, of the wax. So you've got this wax, it's a solid, there it is. But it gets hot, and what does it turn into, this vapor? And these are carbon molecules, long carbon molecules, and they're drifting up into the air, and it's hot enough that they can react with oxygen. So the oxygen's coming in, and it has to react just the right proportions to completely combust it into carbon dioxide and water. And if it did that completely, there would be no color. You wouldn't see anything, because carbon dioxide's invisible, and so is water vapor invisible. But yet you see it. So what's going on? Well, look at the blue first. The blue is where you've almost got perfect combustion, but you still have a little bit of color. And what that is these free radicals of carbon and hydrogen that are just about to become carbon dioxide. And as they're doing that, they're vibrating and absorbing some light. And that is the blue. But the rest of it's yellowish, right? Reddish yellow. What's that? Well, that's imperfect combustion. So these carbon molecules coming off from the wax, they react with a bit of oxygen, they become carbon dioxide, but most of them don't. And so they become carbon, little bits of soot. You know that about soot. And that soot then glows white hot, or yellow hot in this case. And it's the glowing of the bits of soot that are the flame that you see. And then above a certain point, it gets too cold to glow, and so the flame seems to have an edge. But there's still vapor up there, as you know, if you ever put your hand over it. So if you turn it out, of course, what happens next is that you get this smell in the air. What's the smell? It's the uncombusted wax vapor. Now, you can tell a lot from the color. We just talked about it. But you can tell some other things. There's this thing called spectroscopy that grew in the 19th century from these kinds of observations that Faraday was making, which is that if you really look at the color of flames, you can tell stuff that's going on in terms of the chemistry. And I'm going to show you something else about that now. I'm going to just blow that out. And I'm going to turn the lights. Oh, no, we can keep the lights down. Hold on, let me just do this blowtorch. Okay. Now, this is a blue flame. This is butane. and we've got that radical, right? So it's perfect combustion, very nicely optimized, but you're seeing that radical, slightly blue tinge. And now I'm going to put some safety on, and I'm going to show you, like, if you squirt certain things into this flame. All right, so that looks just like a normal candle flame. But actually, if you look at it very carefully, the light's slightly yellower than that, and that's sodium. Okay? This is the copper. So we know that there's copper in this flame. And sometimes when you have a fire, you can see that coming out, little copper things. What about this one? Lilac. And that is potassium. So we can tell the chemistry of the liquid by looking at the colors. And this is really incredible because, whoa, anyone know what that is? Shout it out. Strontium, you're good. Okay, so, yeah, there you go, let's hand it to the spectroscopy and Faraday. So, if you're wondering how we know that there's hydrogen in the sun, and how do we know there's calcium in the sun and sodium in the sun, it's this. Because we know we can make the chemistry here on Earth, we can study the color, the spectrogram of each of the elements, and then we look at the sun's light and we compare the two. And actually, what happened then was, when people got the hang of this, they realized that there's some elements in the sun that they had never seen on Earth. And those elements people started looking for. And that's one of the really great stories of the periodic table, is finding stuff in the sun because of this experiment, because of spectroscopy, and then just searching the Earth for them, and filling in the gaps of what we knew. But that's for another time. We haven't got time for it now, because I've got about 200 demos to do for you, and I know you're going to want to see them. Okay, so now, what is a gas? That is, we said that the flame is a kind of gas phenomena, and this is some liquid nitrogen, by the way, in here, and I put in some balloons earlier. I'm just going to take them out, and the thing about them is, if you have a look at that one, is that they look very flat and annoying balloons. And some of them do things like, they warm up and they go up. And some of them warm up and they go down. And there's some more in there. Come out, come on. All right. So, look, if I put it in there, if I push it into the liquid nitrogen, I'm getting it colder and colder and colder and colder and colder and colder and colder. I bring it out, and then, it loves the liquid nitrogen, this one. Look, there's one, really cold. Now, there's gas in there. You wouldn't believe it. It's warming up, and that's what's happening. So what is a gas? It's molecules, individual molecules or atoms, and they're running around. They're on their own, and they've got energy, and they just run at the balloon, and they bounce back, and they run at the balloon, and they bounce back. And that's the pressure that you feel in a balloon. It's those individual molecules running with energy. But if you take that energy away from them, like we've done here, well, they can't run anymore, so they have no pressure. They have very little volume, because volume and pressure are related, and temperature. So it's these combinations of temperature and pressure and volume which are kind of the core of just the basic ideal gas laws. And you can do it back and forth, back and forth, back and forth. And that's what you sort of don't realize, that when you live kind of at the temperatures that we live, we don't experience this in every day. That's why you have to cool it right down. But the fact that most gases, right, the ones you're breathing in now and out now, they're mostly nothing. They're a tiny number of molecules. Look, that's the proof of it. Look how little there is in that until you warm it up. And its volume is just to do with its temperature. It's just because we're giving it more and more energy. It's not because there's more stuff there. There's the same amount of stuff there because the balloon is fixed. So this is the incredible thing about gases, and it's different from other forms of matter. But of course, you've noticed something else here, which is that there's another aspect of those molecules that we haven't talked about yet, which is that some of these are denser than air, so they fall, and some of them are less dense than air, so they rise. That's called buoyancy. Now, this is the same buoyancy that you get in the sea in any liquid, right? Any fluid will have buoyancy. If you're less dense than the fluid you're in, right, you float. If you're more dense than the fluid in, you sink. water, air, everything. Now, we've sunk to the bottom of 100 kilometers of air above us. We are at the bottom of a sea of gas. It's our atmosphere. But these, they are not more dense than it. They're less dense. Anyone want to guess what these are? Helium. What else could they be? I mean, that's a definite possibility. So they could be helium. Helium is less dense than air. We see it occasionally. Could be hydrogen, right? That's also less dense than air. Anyone else? What else could it be? Huh? Methane, yes. Brian, thank you. I knew you'd do that. Methane is less dense. There are not that many, actually, sort of naturally occurring elements. Carbon monoxide. And then nitrogen is sort of neutrally buoyant, almost, but it's not really. Okay, so let's say we think it's one of those, and we're going to see if it's not helium. And I want to sort of do this, and think that through, really, by having two of those. Okay. Let's just take one of them away for the moment, and we'll bring it back. Okay, now I need to hold on to this in a safe place. Yeah? Yeah, go on. Helen, thank you very much. You hold it. Please don't let go of it. Otherwise, there's all sorts of health and safety issues. Okay, so if this is hydrogen, we think it will do what if I introduce a flame to it? Explode, because it will react with oxygen in the air with a bang. So let's try that. But just in case it's helium, what will that do if I put a flame on this? Nothing. The whole thing will just sort of burst. The balloon will burst because I put a flame on it, and the rubber will melt, and then the helium will go off into the atmosphere and actually go into outer space eventually, unfortunately for us. And we need the helium, so we hope it's not helium, don't we? Okay, now what I want you all to do is not going to be a massive bang, if it is a bang, is just to put your hands over your ears in case you get some sort of ear damage. Okay. Is it helium or is it hydrogen? Oh, okay, it's hydrogen. Okay. Thank you very much, Helen. And we shall just see if this one is helium. So difficult to tell because they're invisible balloons. And, the gases. The balloons are not invisible, obviously. And so this could still be helium. It could be methane, Brian. What would we say if it was methane? What was the color of that flame, anyone? Orange. Now, do we think that's because, why do we think that is? Huh? The balloon? Anyone else? Incomplete combustion, probably. Right? So the hydrogen's all in the balloon. It suddenly goes out. It has to meet the oxygen. It starts getting, as it reacts, it gets depleted. And so it's not going to, but then what would cause the yellow? Well, probably a few little specks in the air. And they would glow. Okay, ready? Hands over ears. Thanks. Everyone good? Is it helium? No, it's not helium. That would just be too boring, wouldn't it? Okay, right, so we've got the hang of gases now. Candles are important, and they're also a lifesaver at dinner parties. Balloons can tell you a lot about what gases are. And we've got the hang of the fact that there's this thing called density, and that really comes from the individual weight of individual atoms and molecules. So atoms actually have a weight, and they are very different from each other. And so the air that we breathe, which is a mixture of molecules, its combined density is, well, it should be neutrally buoyant, but you've got the balloon as well, so it's more dense than air. Okay, so we made an explosion, and that created a wind. And that, of course, once you know that, you sort of think, well, what can we do with him? It's a pressure wave. Surely we can use it to make some technology. And the early Greeks had the same idea. They thought, okay, we're not going to make hydrogen. They didn't really know what hydrogen was. They were still in the fire is an element phase, but they did know how to make another gas. So in here is a can with a little bit of water. And this is the top, and they didn't do it with a golden syrup tin. But it's a guy called Hero, who was an inventor, an incredible Greek inventor. And he invented the first steam engine 2,000 years ago, approximately. And I'm going to show you the basic principle here. So water goes in there. We're going to heat it up in a minute. It's going to become steam. It's going to come out these two things, but they're in opposite directions. So we can use this principle of making a gas and the energy in a gas to drive something, a little engine. We'll give rotation anyway. Okay, let's just get these on. And yeah, okay. All right. Now, the thing about heating up water in a pressure canister is that if it releases in the wrong place, yeah, you obviously get a bit of you don't get what you want. But the other thing is that you require a lot of energy. And this was one of the big problems of these Hero engines, is not that they didn't work, because in a minute, hopefully, we'll see that there'll be steam coming out of these two tubes. So they've got a little bit of water coming out now. There we go. And there it goes. Yes! Let's hear it for Hero. That is where the word hero comes from, by the way. And but the thing is, you had to heat. So if you're going to use that to rotate something, let's say to grind wheat or to pump water, you've got to use a lot of energy. And in those days, 2,000 years ago, energy was not cheap like it is today. Energy was expensive and difficult, and it was actually one of the things that kind of held civilization back was access to, let's say, wood or oil or any of these things. So it was not a trivial thing. Nevertheless, come on, if you can grind some wheat with that, that sounds great. But why bother when you have a free source of gas energy? And that was the wind. And so let's just go to the first slide, if you don't mind. So the wind, right? The wind, of course, humans are so smart, and it's not only the humans that do it, but this is a Polynesian, very early, at least 2,000 years, design for a boat, a ocean-going canoe. I believe Helen has actually sailed in one of these. And they're incredible. That you can make them off the materials of an island that in the Pacific. Now the Pacific is a third of the ocean, a third of the world, and it's basically a water world with small islands. And they learned how to get between these islands, which were hundreds, thousands of miles apart. And they did it with the wind. And they learned how to harness the wind. You don't need to have loads of fuel and steam because the wind's blowing. And it blows in predictable patterns in the earth. And they were experts. They still are experts. And in fact, not experts in just harnessing the wind, but actually using dead reckoning and understanding how far you've got in the wind by how fast it's blowing. So no technology to work out whether they've gone 50 miles or 100 miles except their own senses. And that really is extraordinary. And we've sort of lost that as humans, and it's a real shame. Next slide, please. So you've got sailboats. This is about 1,000 years old, still going today in Iran. These are the early windmills for grinding corn. So underneath are the corn stone, the grinding stones, and these are vertical. So the wind blows through, and this is an area where it's very predictable wind, and then it goes through those wind turbines, and they rotate. And so just again, wood and kind of tree trunks, but it works, and it's free. And of course, it kind of proliferated across the world. Next slide. So wind power really powered the kind of exploration of the whole world, and it brought trade in. If you want to move goods from one place to another, or if you want to dominate another person, or if you want to invade them, of course, you use wind power. And look at the size of these boats. They really aced it. Next slide, please. Yeah, and windmills were everywhere too. They were used for grinding wheat and barley. They were used to pump water, to make the Netherlands into what it is today, and to make lots of places like Norfolk, basically to pump water out. They were just the brilliant gas technology. And that was all the way up until the 19th century. And then what happens is that someone has an idea to go back to steam. Why would you go back to steam? But they want to do things where the wind doesn't blow. They want to have instant power when you want it, right? And that really resonates today with today. You know, we're all used to that, a flick of a switch. But they really didn't live in that world. But it was alluring, and the steam engine just seemed to be, every inventor went back to the steam engine. How can we get it to actually work? And everyone failed. And the person who succeeded, and it's not an alone invention, it's loads of people's work, but he's often kind of credited as getting the first working one going in a mine, is Thomas Newcomen. Now, I'm going to just show you what he did, and it's not using this bit of the steam. It's using something else, and it's sort of surprising, I think. Okay, so I'm going to need this water over here, and we're going to need this on. So this is a butane. We're going to make some steam in this little canister here, and but we're not going to use the power of the steam squirting out, impressed as it is, Hero. We're not going to use that force. We're going to use a different force, but it's still a steam force. So I've got a little bit of water in there, and in a minute, you're going to hear it. Well, okay, can you see that steam coming out there? Yeah, maybe. All right, now I'm going to do this. Trap the steam in there and cool it. And what happened there is that the can crushed. And now why did it crush? Because 100 kilometers of air above us decided they didn't like that can. Crush! Because that air has a weight. That air has, you won't believe this, 1 kilogram per cm squared. So a centimeter squared is like your thumbnail. There's 1 kilogram of weight weighing on that, and the rest of us. Now, we're used to it. We grew up in it. We were born at the bottom of this ocean of sea. This can was also born there. And before I threw it in this water, it had air inside it. So the air pressure inside was exactly meeting the air pressure outside, and so the can was fine. Then I put the steam in it. And again, the steam regulated its pressure, because it was open at the top. So the steam pressure was now pushing back on the air, like that. Then I put the top on, like that. And now the steam isn't being generated anymore. Then I cooled it down, and it became a liquid, and now there's a vacuum inside. And now the angry gods of the air crushed it into a small part. So I was going to do that again, but we need to crack on. Now that steam power, oh, damn, I wanted to show you something else about steam power that's really important. Or maybe I'll go to I'm going to put this on here. This is our house kettle, by the way. And the other thing that's brilliant about this, so this is called atmospheric steam engines. Basically, what Newcomen did is he took a cylinder, and instead of having it crushed, he had a piston be pulled down. So every time the water steam inside was condensed, it sucked it down, or in fact it was pushed down by the atmosphere, and then he'd push steam back in it, it'd go up, and then he'd condense it. Up, down, down. And the steam engine's born, and it's very inefficient, and there are loads of innovators who do better than that. But if we go to the next slide, what we find eventually is that the killer app for it, even though it started off pumping water out of mines, the killer app wasn't pumping water out of mines. It was transport. And why do you need it for transport? Well, we had sailboats on the water, but actually what people really wanted to do was get around on land. And to get around land was a very clunky way. You're either on a horse or in a carriage, and they were both quite uncomfortable, and they're both quite slow. And not everyone had access to it. But when the steam engine comes along, the friendly toot-toot. Doesn't that remind you of steam engines? A little bit. Or camping trips. Which one? Toot, toot, toot. Now that's the sound, everyone, of freedom. That is the sound of holidays. Because before this, what a holiday was a holy day. You got a day off from the fields. Everyone works in the fields. 90% of people worked in the fields, and most people were poor, and all of us here would have been basically dirt poor and working on the fields, pretty much, except for a couple of people in the front row. And then the steam engines come along, and the thing about them is that they only work when everyone goes on them, right? There's no point having a railway system that's for only 2 people, because you've got to put a lot of infrastructure down, all the rails. And so you have to have hundreds and thousands of people on it. So the railways come in, 1820s, and the first railways are sort of introduced. Everyone thinks it's like a novelty. And then they realize they can go to the seaside for a day, trip, and come back. And people just love it. Like they've never seen the sea before. And suddenly the seaside holiday is born in this country. And if you go to the UK seaside, there is a very particular seaside architecture there. And that is born of steam. That is the steam age, writ large. And it's still there today, and I hope we kind of hold on to it. So basically, steam didn't just mean working long hours in industrial mills and times were hard. And that was true too, the textile mills, but it was also freedom. And that's what gas technology does for you. And so that started the whole spark of invention, which eventually led to the car. But it was, in fact, the steam engine on the locomotive that really ignited that desire and made it possible for everyone. It's a sort of real, it's a real technology for us all. Okay, so now, changing tack a little bit, because there's another gas. So once, and it is industrial Britain that does this. There's a whole load of inventors who are starting to look at how to engineer things with gases. And this is solid carbon dioxide, by the way. But it's just an effect. I just want a spooky effect. I shouldn't have done that first. Okay, I want to do this. That is just detergent from our kitchen. There's quite a lot of stuff from our kitchen here. Okay, now, all the while that progress, let's call it progress, it is progress, is happening with the railways and the steam world. All that while, people have been walking past boggy places and misty places and noticing that there's this strange stuff that bubbles up occasionally. And they called it things, and they've been calling it things for thousands of years, because occasionally it would ignite. And I want to show you that too. And we're going to need the lights down for this. Ooh, that is too much. I put too much in. All right. Oh, that's good. All right. So stuff bubbled up. What was it? No one knew. It smelled bad, though. Oh. And it would suddenly, sometimes, just burst into flames. And these were called will-o'-the-wisps. And there's a language for will-o'-the-wisps everywhere in the world. They're a phenomenon. But they weren't thought of as a natural gas phenomenon at the time. They were thought of as spirits, fairies. And some of them were good, but most of them were bad. And they would lure you to your death. And if you saw a will-o'-the-wisp, you mustn't go to them. But many people did, and they died, horrible deaths. So what was this? And in the end, the gas technologies, people start to work out, it's actually methane coming out of the bottom. And methane's flammable. And so this idea that there's these gases being boiled up by the earth, and they're popping out all these different places. What could we do with them, people thought? Surely they had some use. And of course, they also exposed themselves to them another time, and that was in the mines. So there's things called damp gases and fire damp mine gases. And they were killing people because these same gases were popping up in the mines, making the coal for the railways and for everyone. And they were killing loads of miners by exploding, as I just showed you. And so this whole industry of mining coal for the railways, for the steam age, for the industrial age, suddenly collided with this kind of age-old kind of worry about these weird spirits down the mines, in the marshes. And what the first technology was protection against them. And so how to stop being killed by the will-o'-the-wisps. And this is going to give you some idea about it. So I'm just going to show you this piece of technology. This is, in a minute, I'm going to light this candle. No, not in a minute, now. I'm going to light this candle now. Now, you imagine you're in the mines, and this is your candle for digging out the mine. You're very poor. You're very poor. Okay, but you like it. You like it. Sometimes you like it. But this day is bad because there's some mine gas in there. And people, it poisoned people, it suffocated them, but they would, of course, because they got candles, naked flames down there, it would ignite. And then there would be these terrible fires, awful fires. And so people like Humphry Davy from the Royal Institution would start to develop technologies to try and save the miners. And one of them are these two gauzes that you see in the middle of this here. And the idea is to try and stop a flame once it's ignited from getting through to you or to your mates. And so what I'm going to do is I'm going to pump a bit of mine gas in there, butane in this case, and it's going to push along here through the gauze to the candle, and then it's going to ignite. And then we're going to see if it makes it through these gauzes, which is the key technology for saving the miners and for really understanding how to control methane. Maybe we want the lights down a bit. I need to not stand in front of it. Okay. All right. Everyone okay? Okay. So this bit didn't ignite. Yes. So this bit didn't ignite. Now, let me show you what happens if you don't have this technology in place that Humphry Davy from the Royal Institution and others, there's quite a few around the world looking at it. Let me show you what happens if you don't have that in place. Okay, candle on again. And this was the reality of people's lives. It was incredibly dangerous working down the mines for all sorts of reasons, being flooded, these terrible gases. Okay, right, let's try again. Sorry. Okay. So, Humphry Davy, the Davy lamp, here it is. Actually, not the actual one, but the actual one's downstairs. And this is where it was invented. And this is just a very exciting thing to be able to show you. So instead of just having a naked flame, you had a flame like this, and a lighter, and you would light it and go down the mines. Ooh. But then you've got this piece of gauze on the outside of it. Exactly this sort of gauze that we show it here. And the thing is, the flame can't go through it. I want to show you this, actually. So see this candle here? Hasn't grown very high yet. But, right. So this is the dinner party savior. Is if you have a piece of gauze on you, you can show people this. Which is that the flame won't go through the gauze. Look, it squashes the flame, even though it's just a piece of gauze. So it's a metal gauze. Right? The gas can go through, it is going through, but the flame's not going through. I mean, that's a piece of magic. Now, how did they work this out, and what is happening? Well, it's all back to that thing. There's a vapor is flammable. There's oxygen that's going to react with it. But you also need this extra other thing. You need a particular temperature for that reaction to take place. And the heat is all being dissipated by the gauze. So it can't get to the right temperature. So beyond the gauze, the temperature's too low for ignition. And that's what happened there. Beyond that gauze, it was too low for ignition. And there it is. So if you have a gauze over your candle, like so, and then you get, how are we doing? Okay, you've got to see this one. Then you get some safety goggles on, gloves, yeah. So let's get the mine gas into this balloon. So like this. Okay. And now I'm going to waft it. I'm the miner, making a good living, enjoying it actually. I play brass instrument. See? And that went fine, didn't it? And let's show me, if you didn't have that, the same experiment. Without the Davy lamp. Okay. Put this on. Okay. All right. So that was the difference, life and death. Life and death. An invention from here, the Royal Institution, and understanding methane and the damp gases and the will-o'-the-wisps. So, okay, that's saving lives. But then people are like, oh my God, hold on a minute. If we could control that, it's like flammable gas. Why can't we sort of make it in a kind of industrial way and then pipe it through places? And if we go to the next slide, I think, yes. So what people thought was, let's light the cities with this gas, right? Well, it won't be a will-o'-the-wisp that lures you to your death. It's a will-o'-the-wisp that lures you to shopping. And I'm not joking you. It was mostly funded by people who wanted people to shop at night. And if you look at London, Why is it so alluring? It's the lights. The lights make it so alluring. And you've got to remember, this country, for 6 months of the year, is just dark and depressing. And the other 6 months of the year is sometimes dark and depressing. But the gas saved everyone. And they started pumping. It was really dangerous. You see how dangerous it is. There were loads of leaks, and they didn't have a way of metering it, so they had to get around people. Literally, people's job was to look through people's windows and see if they were using it, and then they would say, okay, you owe us 2p. That is literally their job. And the other people were the lighters. So a lamp lighter was a really good job, and you went around as dusk happened, and you lighted all the lamps. And in case you're thinking, oh my God, this is all gone since electricity, it hasn't all gone. If you go to Hyde Park, there's still gas lit. Hyde Park is still gas lit by the same lamps that were put there 150 years ago. It's really magical. So gas lighting, right, it really changed cities. People were far less scared. And this darkness was a big oppression for people. And gas lighting, even though it was incredibly dangerous, was just too alluring. So within 20 years of the first gas lighting being put onto Pall Mall, that was the first one in the street in London, any city in the UK above 100,000 people had gas lighting within 20 years. So that's just how much they thought it was the future. And they were right? We wouldn't put up without street lighting. If you go to the next slide, you can see the big gasometers, right? Even as a kid, I remember these. They were sort of still operational. That's where they stored the gas. And why did they have to store it? Because it was all used at night. So they had to make it during the day, and then they stored it in these enormous things, which now are Shishi Flats in King's Cross, not so far away from here. But they used to be in every town. In every town, there was a gasworks with these enormous, wonderful structures. And they're a very ingenious way of storing gas, which I can't tell you now, but we will get to at some point, because, shit, what should I write down here? Are we doing okay? Okay. Mm-hmm. All right. So, the smell of gas. Right? The smell of gas. You can't smell it, can you? There is a smell in this room. It's not that smell of gas. And that's because methane doesn't smell, and neither does butane. They're odorless. And so the funny thing was the early gas lighting was really smelly because it had things like hydrogen sulfide in it as a byproduct of getting the gas out. And people hated it, and so they spent a lot of time and energy getting it out. And then in modern times, it was so clean, and today it's so clean and so odorless that you don't know you have a leak, and that's really dangerous. Not a week goes by without a massive building blowing up somewhere around the world because of a gas leak. It's true. And so they put in this little gas molecule, this smelly molecule called methylthiol, and that is that sort of garlicky, next time you smell it, think garlic. It's a garlicky smell, and it's an intentional additive, okay? That's what it is. But it's also, if we start thinking about the smells of gases, it's also a good way to sort of really think about that part of the gas world. Most gases are odorless, but not all. And if we go to the next slide. Oh no, I haven't talked about gas lighting, of course, because the term gas lighting comes from a play about gaslight, which was put on in 1934, but it was set in 1880, and was all about this guy who was pretending that the lights were flickering and going on and off to his wife to make her go mad. And so this is where that term comes from, gaslight, actual gaslight. You may think it's got nothing to do with it, but it does. Okay, next slide. Okay, so what's that? Is that orange? Does that look orange to you? Okay, what planet's that, do you think? It's in the solar system? Venus? No. What? Saturn? No. Mars, close to Mars. It's almost like Mars. It's not like, it's not here today, that planet, but it kind of is. It is, it's in a different form today. That's what this planet looked like 4 billion years ago. Earth was orange. That's weird, isn't it? Earth was orange. It was a pale orange dot in the solar system. Why? Because its atmosphere was methane and hydrogen sulfide, really smelly. It was nitrogen. It didn't have almost any oxygen in it. So what we know is that the early atmosphere which basically pumped gases from the volcanic eruptions and so on, because Earth was kind of active. And that's one of the key things. Active planets have an atmosphere that keeps pumping gases out. And then to keep hold of the atmosphere, you have to have a magnetosphere. You have to have a magnetic field. And Mars lost it, and we think it was very like Earth, right? We think it was full of oceans and had an atmosphere, and it lost it all because it didn't have a protection from the sun's wind. But Earth went blue, right? We became a pale blue dot. But we had no oxygen. Now the question is, what does that mean? What happened there? And I want to show you something about why oxygen is so important. And maybe I'll just go to the next slide first. So we don't know how life started 3.5 billion years ago. There's some sort of moment over here where the single-cell life forms happened. Prokaryotes, very simple little blobs, a single membrane with lots of little stuff going on inside. And there was no oxygen. You can see the oxygen levels were very, very low, right? That's that line there. Then we go forward 1 billion years, 1.5 billion years, nothing's changed. And then suddenly there's a massive great oxidation event. Suddenly oxygen comes in, and it's because these things called cyanobacteria learn how to photosynthesize. So before this, the cells are taking energy from the Earth's undersea vents, something, sulfurous, hydrogen sulfide, things like that. Then photosynthesis comes along, and they can go anywhere in the ocean where there's sunlight, and they can turn CO2 into energy. And they give off oxygen. And it's because none of the other life forms have ever seen oxygen before, they all die. So there's a massive extinction event, except for a few of them that don't die. And the ones that don't die have all these protections against this strange gas, because oxygen's incredibly reactive, which we'll see in a minute. But look, what happens to life at that moment? Suddenly life gets really complicated. Suddenly you get these eukaryotes with nucleuses inside them that do all sorts of different functions, and they're protected. And then nothing happens. For another 1 billion years, right? Single cells, but complicated single cells, happen, and then boom. 500 years ago or something, there's another oxygen rise. And that, we think, is something to do with the rise of plants, fungi, animals, us, lot. And to have this amount of complexity, there is some correlation with the power of oxygen in the atmosphere. And if you're an alien looking at our planet, and you see oxygen in our atmosphere using spectroscopy, you're going to think there's life there. Because oxygen's so reactive that if it wasn't constantly produced, we wouldn't have an oxygen atmosphere, because it will react with everything and then just become a rock, basically. And all those, you go to the beach, all those lines you see, all that iron oxide, that's all because oxygen was bubbling up and just reacting with iron and silicon and, sand, silicon oxide, iron oxide. And that's what happens, right? But no, we're constantly pumping it out. So let's just see how reactive oxygen is and why it's such a special gas. I'm going to try and pull this over here so it's in the middle. Okay. Now, thank you, Jason. This is, thank you very much, liquid oxygen. Now, the oxygen we're breathing in the air now is, thanks. Actually, let's move that around. Oh, thank you. Thanks a lot. So the air we're breathing is a gas, obviously, and this will become a gas very soon. But before it becomes a gas, we're going to put it on these potato snacks, onion snacks, which their main reason is that they're carbohydrates, so they are basically fuel. And oxygen will react with most things, including carbon molecules. I'm going to pour the liquid oxygen on them, and then I'm going to light it. And you will see with your eyes just how special oxygen is, like how much energy it releases if you give something unlimited oxygen. And if we did it to you now, you would burn as brightly as this too. Okay, are we ready for this? Have I got all the safety gear? That's the big question. All right, now liquid oxygen this is also a lifesaver, by the way. I mean, this is made every day, 24 hours a day in this country. It's made for the hospitals, and it's shipped 24 hours around. And COVID Without that, thousands more people would have died. It was the only therapy available, so oxygen, and it's amazing stuff, because we breathe it. And we breathe it because we need it. Okay, this is how good it is. All right, it's blue, by the way. I should have showed you that. Ready? Ooh. Oh. It's boiling away. Oh. It's too cold. There we go. Life, everyone. So something to do with oxygen coming into the atmosphere and life using that power is what fuels complex beings, is the basic hypothesis. And the reason why big stuff like us breathes oxygen is because we need to. It allows our metabolisms to be as powerful as they are. It allows us to think. It allows us to do all the stuff we do. It also does the same for plants, right? Plants are not just giving out carbon dioxide. They're multicellular complex beings too, and they breathe oxygen at night. So this is a key part of our world and of our living world. And so now I want to talk about, yes, good, okay. So we're breathing, and I'm going to breathe into this balloon. What's in there now? Is it oxygen? I mean, it's mostly nitrogen, isn't it? Because the air is mostly nitrogen, 78% nitrogen. So it's mostly nitrogen, but I've breathed out carbon dioxide. How much? Is it like, have I used all the oxygen? Are you willing to bet my life on that? If I breathe this in and collapse, it's your fault, okay? Who thinks I should breathe this in? You always do. Okay, you're a very clever audience. Okay. Fine. Okay, now, yeah, you're not using all the oxygen, which is why you don't run out of oxygen at night, even if you're if you don't open the windows. But you should open the windows, because you get slowly poisoned. So do open the windows. But look what else happens, though, when you breathe out into a balloon or any other elastic substance. You get this just other side of gases, which is this, it's just fun. It's just mad. It's just like they've got this solidity, and we know if we put this in liquid nitrogen, it's only like it'll go down to nothing. But then, at our temperature, look at this. And what holiday is complete without one of these? Like, I tell you, like, this is an important part. Like, gases not just make us live. They're not just absolutely vital. They are really joyous. And here's another example of it. Yeah, thanks. That was, all right. All right. So not only do we love them, but we want them in our drinks. And why is that? Because we don't have to have them in our drinks. Like, no one's forcing us to put them in the drinks. But they just make a drink better, don't they? Now, beer without fizz, which was how most people drank it back in the day, is just not good. But also, that a beer without a head, without a foam, this is no good. No good. You don't enjoy it as much, do you? If you get one like that, you're like, something wrong with what? Beer, maybe, or the glass. So partly it says cleanliness, doesn't it? It says everything's good. Like, this is good. This tells you that beer's good. You're going to feel good. And look, it's fizzing. It's fizzing, and it feels alive, and it's like breathing. Like, the drink is breathing, and it's got this frothy stuff on it, and it just is alluring, right? So that's how we think about beer when it's a proper froth. Now, if the reason why that's a froth, of course, is because carbon dioxide is coming out of the liquid. It's then interacting with these sort of polypeptides from the beer-making process, which change the surface tension. So this is not just like water, as you can see. There's no detergent in here, but there's something acting like detergent that's actually delicious. And it's these kind of complex polypeptides. And they change the surface tension just like a detergent does, so you get a foam. And it's quite a stable foam. And hopefully, it's sort of, oh, I won't do that now. But anyway, but if you can disturb the surface tension, and I'm just going to show you that. So if you put things in there that basically change the surface tension, the foam initially starts, but then just disappears. And that's no good. We hate that, okay? And so there's a lot going on. Beer makers have to be really careful of this. And in fact, Guinness, a while back, sort of started putting nitrogen little capsules in there to make sure they got exactly the right foam. But here's the odd thing, and this is the moment where I realize I haven't got enough glasses. I'm going to put that in there. Okay. Is that okay? What I need is a volunteer to try the type of fizzy drink that doesn't have a foam and has exactly the opposite effect if you have one. Now, I need someone who is prepared to drink Coke straight from the bottle. And I'm going to call on someone who's already been vetted in terms of health and safety. I can see him in the front row there. He's signed all the forms away, and even though this is a very dangerous experiment, this is Laszlo, everyone. Now, so if let's come around here, I just realized that we're not in the right place, are we? Is that okay? This is good, okay. Let's take this down. You hold that. This is one of your friends, isn't it? Coke. Now, just holding a Coke bottle, talk us through it. Does that make you happy?
No, because I haven't got a glass.
You haven't got a glass. But hold on a minute, I'm offering you something better than that. The freedom to glug. No, look at your eyes. Now, in a minute, I'm going to ask you for a evil laugh, but not yet. At the moment, we're in the joyous phase of this experience. That sound, what did that sound do to you? Like just the sound of fizz. That's a gas sound we love, right? Yeah. If it didn't exist, you'd feel upset. And now, what's happening inside your brain now? Is delight happening?
Yes.
Okay, I'm going to pour it into this because I want to show everyone something, which they already know, so I don't know why we're doing it. But look at that. The foam starts, carbon dioxide is coming out, but then it disappears. And are you upset? Do you think that's a bad idea?
Not really.
In fact, if the foam persisted, would you hate it? You'd think there's something wrong with this, wouldn't you? And you say, Dad, you try it first. Now have a glug. Talk us through this process, come on. Oh.
Well, it mainly tasted WD-40.
Oh, God. It's too... Okay. All right. All right. Now, let's see if we can get this demo right, okay? This is the classic demo where we put some Mentos into, these are mints, and you've probably all seen it on YouTube. You throw mints into this, all the carbon dioxide immediately erupts, and this thing goes into the air, and everyone in the front row just gets soaked. Evil laugh. Sorry, good. Do it again. That was a good one. I think it's the first one. Okay, but we're not going to do that because we thought something better. And together we developed this demo to show you how much, because you saw how much gas is in a balloon, but we want to know how much carbon dioxide is in here. We want to see it inflate a balloon. So what we've got is some Mentos in there. In a minute, Laszlo's going to take this. I'm going to take that. And you're going to tip them. They're in the balloon. And he's going to hold on to the balloon. You're going to hold on to the balloon. Yeah. And then they'll all go up, and then we'll see how much carbon dioxide comes out. So you have to tip that over, and then we have to... I'm going to give this... Dan, can I give this... No, I'm not. I'm going to hold this. Okay, I'm just a bit worried. Hold this off of the balloon. Oh, I'm going to hold the balloon. Okay, you go. Okay, Mentos in. Oh, they're not in. Oh, they're stuck. Okay. And it's coming up. And the carbon dioxide is lifting us off the ground. No, it's not, no. All right, but give it a bit of a shake. It didn't work quite as well this time, did it? No. Okay, well, anyway. We're working on that. One of the things we also wanted to say about this demo is it's telling you how much carbon dioxide is in there. That's all carbon dioxide there. But it's also kind of addressing another issue about climate change, isn't it? Like, carbon dioxide is funny, it's wonderful, it's fizzy, it's great, and we love it, but it's sort of causing climate change. And that's back to the steam age, right? We started the whole thing going, and now we're reaping the things. And so what we need to do is capture the carbon dioxide, and this is a brilliant way of capturing burps of carbon dioxide before you even drink it. In fact, you could capture some of the carbon dioxide from the fizz before you ever have to drink it, and you'd feel less guilty. Do you feel less guilty?
No, I feel like you've ruined my Coke.
Okay, that's right. You've ruined the Coke. All right. Thank you, Laszlo, very much. Great. Laszlo. Okay. So, where are we? Oh, we're close. Okay, so, oh man. Yes. Hydrogen balloon, right? So what we need to do now is start talking about different ways. I mean, flying basically gives off tons and tons of CO2. So if you want to do one thing, which is to reduce your CO2 emissions, just stop flying, or at least only fly once a year. See if you can do that. But if we go to the next slide, what we realize is that actually there are other ways of getting around via the air that were developed 100 years ago. And these are called the Zeppelins. And they were an incredible thing. And I'm just going to see if we can get this hard. Yeah. And what basically the Zeppelins were, these enormous airships, huge ones, and they were the beginning of flight. The first airline, thank you very much. The first airline, yes, brilliant. The first airline was a Zeppelin, and it was inflated with hydrogen. And why hydrogen? Because it's so much more buoyant than any other gas, more than helium. But not just that, it was cheap. You can make, I mean, that's a cathedral, literally a cathedral full of hydrogen. And so people started flying across the Atlantic. They flew down to South America. This is a picture of the USS Los Angeles. I mean, I'm skipping over the big history of them being used as a weapon of war and bombing London, and you'll see lots of things around London. I'm not saying that was all not terrible, but it's also just an incredible testament to what people's initial vision of what flying would be. And the great thing about airships is that they're neutrally buoyant. So once you get up there, you don't have to expend energy being in the sky. And I want to just show you that. So look, this is trying to get up to the roof. If I start adding little people to this Zeppelin, then, God, it only takes one Lego person. Okay, well, it's a very expensive flight. And it was expensive. Like, to cross the Atlantic was £28,000 in today's money. Okay, so we've got one. I think that might even be very close there. So that was the big deal. Basically, you had to sort of pump hydrogen into it. They had these massive hangars to hold it overnight. And then, and then they would basically let go of weights, and the hydrogen would go up, and then you just adjusted it during flight as pressure changed it. So they vented hydrogen. And the only trick was you had to go somewhere where there was hydrogen-making facilities. But that was another really good reason to use hydrogen, because actually you can make hydrogen anywhere. You just need sulfuric acid and some iron. And actually that turned out to be not a big deal. The alternative gas, which is helium, which we'll talk about in a minute as we finish, I promise, it is really hard to get hold of and is also in very short supply. So hydrogen makes a lot of sense for flight. There is one problem. And I need a stick for this. Thank you very much. And a lighter, yeah. Okay. I'm just trying to wait which way around I should do this. I think I should show you the slides. Okay, the next slide. Okay, yeah, so this is what ended hydrogen, really, as a kind of viable thing. This is the Hindenburg bursting into flames. And there were other big disasters, so this is not the first time it happened. And again, like the methane story, people just wanted street lighting too much to stop using this dangerous thing. But this really did spell the end, because not everyone died. There was about 20 deaths out of a crew of 120, 130. So it's incredible, really, if you think about it. Not everyone died. And look at this. It was a huge disaster. And we don't really know why it happened, but of course, there must have been a spark. There must have been some leaking hydrogen. But it sort of does show you the power of gases, and it shows you their potential, and it shows you why they're so alluring to us. But also, we have to constantly think. at the moment, we just have this idea the only way to get around is by planes. And that is a recent phenomenon. We can do better than this. We can be more sustainable, and we really need to do that. But let me just show you, as I finish this talk, what happens when it does ignite. Now, you're going to need to put your hands over your, properly need to put your hands over your ear now. And I am going to need some ear defenders, actually. Now, where are they? Jason, are there any nearby? Maybe I don't have any. He's rushing around. They're coming up, yeah. Oh, thanks a lot, yeah. I just don't want to go deaf. Okay, all right, everyone. This is what happens when you have a lot of hydrogen. Ooh, it's coming towards the flame. You can't hear what I'm saying, can you? Okay, ready, steady. Okay, it just remains for me to say, I'm not too bad. It remains for me to say that we could go to helium, right? We could go to helium, but it's in short supply. And where do we get our helium from? We mine it, turns out. It bubbles up from the ground as a result of nuclear reactions deep down in the Earth's crust. So it's coming up all the time. We mine it out of big holes, and then we use it in medical. It's like absolutely vital for healthcare. Like all those MRI scans, all those CT scans, all cooled by liquid nitrogen. Without it, our healthcare system would be trashed. You just wouldn't be able to do it in the current way. And so if we then start using enormous sums of it to start flying around and to solve the flying problem and the sustainability problem, it's probably not going to be an easy way forward. We probably need to think better than that. But you know, this is why I introduce you to this whole world of gases, which you imbibe all the time, the drinks, the holidays, and let's not forget the only reason you go on holiday is because of the steam engine, and it was invented, and the seaside holiday, and then the inflatable comes, and I haven't even told you about the inflatable mattress thing, where everyone thought everyone would be on inflatable mattresses, and the old mattresses would never happen until the birth rate went down radically as a result of that, and they had to think again, and that's all in the book. I kept the best stuff in the book. So yeah, if you really want to get a much bigger sense of it all, then please, yeah, pick up the book. I want to thank, can I thank you first? You can do what you like, mate. You're the lecturer. I'm the lecturer. I want to thank, obviously, my editors, Con and Ivy, for just, because this took a long time, and they know how many terrible versions there were of it. And Annie, my publicist, who's fantastically brilliant and got me this gig, so how good's she? And I want to thank Jason and Daniel and the whole RI crew, because you've been also brilliant. And you know, isn't this the best place to do this kind of talk? It is in the world, I think. And Daniel, I want to thank. And I want to thank my family, Ruby, Ida, Laszlo, Lal, Dan, and Fee, he's here. And, you know, they're just, you know, without them, life's not worth living. And without you, of course, this lecture wouldn't be the same, because you have been a huge part of the enthusiasm in the room. You've been breathing out carbon dioxide, which I think has added to it a lot. And yeah, thank you for coming. And yeah, it's a gas.
Thank you.